Welcome to today's Explainer. We're going to completely dismantle a pretty common myth about how our digital world actually operates. You know, we often picture the internet as this one giant unified cloud that just magically handles all our data. But the reality? The reality is a fascinating, completely decentralized architecture.
Think about it for a second. Every single day, billions of devices, whether you're streaming YouTube, asking ChatGPT a complex question, or just scrolling through your feeds, are sending absolute mountains of data across the globe. But here's the crazy part. The internet has absolutely no central controller. There is literally no master brain directing traffic. So how on earth do your data packets actually know where to go across countless ISPs, telecom operators, and cloud providers?
The answer? BGP, the Border Gateway Protocol. This is the unseen, underlying glue of the internet. Without it, the entire global network would instantly shatter into millions of disconnected little islands. So today, we're going to look under the hood to see exactly how BGP holds the whole world together. Here is our roadmap for today. 1. Anatomy of the internet. 2. The problem with OSPF. 3. How BGP actually works. 4. Connecting the global backbone. And 5. The future of BGP.
Section 1. Anatomy of the Internet. What it really looks like. To really grasp this, we have to totally shatter that illusion of a single homogeneous internet. The web is actually a giant patchwork. It's made up of tens of thousands of independent networks called autonomous systems, or AS for short. Think of an autonomous system kind of like a sovereign digital state, or maybe a giant gated neighborhood. It's basically a group of IP networks managed and controlled by a single administrative entity. So that could be a telecom provider, a cloud service, or a massive tech enterprise.
And these systems aren't just anonymous blocks. Each one operates under a highly specific, unique identifier called an Autonomous System Number, or ASN. For example, Google is AS15169, Microsoft is AS875, Cloudflare is AS13335. Think of these exactly like countries on a global map. And BGP? Well, BGP is the universal diplomatic language they all use to negotiate traffic with each other.
Moving right along to Section 2, the problem with OSPF. Why not use OSPF?
Now you might be wondering, since internal protocols like OSPF, Open Shortest Path First, are so incredibly fast, why don't we just use them to connect the global internet? Well, OSPF completely collapses at a global scale, and it does so for 4 very specific reasons. First, OSPF requires a link state database that basically holds the entire network map. The internet is simply too vast. That database would be impossibly huge for any router to hold. Second, OSPF relies on flooding updates every single time something changes. Since the internet is globally updating every single second, that flooding would paralyze the entire web instantly. Third, the CPU horsepower required to calculate the absolute shortest path for millions of routing prefixes is way beyond what current hardware can handle. And finally, and honestly, this is the real deal breaker, different ISPs are fierce business competitors. They are absolutely not going to expose their private internal network topologies to each other. So the internet absolutely requires a path vector protocol, one that focuses heavily on business policy rather than just raw speed.
Which brings us to Section 3, how BGP actually works, the path vector protocol.
Okay, so there's a really common misconception out there that BGP just exchanges raw IP addresses. In reality, it exchanges prefixes attached to path attributes. It's not just saying, hey, here is an IP. It's essentially providing a detailed map. It attaches crucial context, like the AS_path, which literally shows every single autonomous system the packet must travel through, or the next hop, detailing the exact immediate next router to jump to. It's really these attributes that give BGP its incredible power.
And when a router receives this rich, detailed information from a neighbor, it doesn't just blindly use it. No way. It processes it through 4 distinct stages. First, the raw updates land in the AdRib-in database. Then, the router runs its best path selection algorithm. The absolute winners of that selection process get promoted to the local RIB database. And finally, those absolute best paths are pushed all the way down into the hardware-level forwarding information base, or FIB, which is what actually moves your packets. This exact 4-stage process, it's happening millions of times a second right now just to load this explainer on your screen.
But how does a router actually choose the best path out of thousands of available options? Well, it filters them through an incredibly strict, rigid funnel known as the best path algorithm. It evaluates all those attributes in a very specific order. It checks local weight first, then local preference, then looks for local routes, then checks for the shortest AS path, and so on, all the way down to the neighbor IP as a final tiebreaker. It's a highly logical, step-by-step elimination process that ensures your router makes the absolute smartest possible decision based on the specific business rules of that network.
Section 4. Connecting the global backbone. Connecting the world. Zooming back out for a second, when you look at major players like Meta, Netflix, Apple, or the giant telecoms, they do not operate in a top-down hierarchy. Like we said earlier, nobody is the boss of the internet. They interact entirely as peers. Google and Cloudflare talk to each other as complete equals, exchanging traffic based purely on mutual benefit.
But physically, how do they actually pull this off? I mean, if every ISP had to pull dedicated fiber optic cables to every other ISP on planet Earth, the cost would be astronomical. Enter the Internet Exchange, or IX. An IX is a physical location, essentially a massive, heavily cooled networking building where multiple ISPs, cloud providers, and tech giants all literally meet up to plug into a shared switch. This allows them to peer directly with everyone else in the room, which drastically reduces the extreme costs of pulling dedicated global lines everywhere. Surprisingly, these massive exchange points, they're often hidden right in plain sight, sitting inside nondescript brick buildings right in the middle of major metropolitan cities.
And because of these exchange points and all these interconnected peering agreements, the global internet ends up looking like a massive, beautifully decentralized mesh. It is highly resilient because there are always alternative paths if one link happens to go down, and it's all being continuously negotiated in the background by BGP.
Let's look at Section 5, the future of BGP, beyond the internet. If we look in the rearview mirror for a second, past internal networks of massive corporate data centers were built using older protocols like Spanning Tree and OSPF. But as cloud computing absolutely exploded, these older designs just couldn't scale. They hit a wall. So modern data centers have almost universally shifted to a leaf-spine architecture. And the protocol driving that new architecture? It's actually eBGP. Yes, the exact same protocol running the global internet is now running the internal networks of your favorite apps.
So why make that massive switch? Because eBGP unlocks some incredible features in a leaf-spine fabric. For one, it allows for equal-cost multipath routing, or ECMP, meaning traffic can be perfectly load-balanced across multiple paths simultaneously. It offers blazing fast convergence, virtually infinite scale-out capabilities, and it plays incredibly well with modern network automation tools. It's a real game-changer. So BGP has really evolved, right? From being just the backbone of the public internet to becoming the universal control plane for modern, large-scale IT. Today, it manages advanced virtualization technologies like EVPN and VXLAN. It handles Kubernetes networking, SD-WAN, and even the high-performance AI fabrics being built right now to train massive large language models. It is literally everywhere.
Which brings us to the absolute core takeaway of our source material today. The true magic of BGP isn't about finding the absolute shortest path. Honestly, if we just wanted that, we'd use OSPF and watch the whole internet crash. Instead, the key to BGP is that it provides scalable, highly controllable, policy-based routing. It allows independent companies to route their data based on human business agreements, economics, and security policies, rather than just blind speed.
And that leaves us with a pretty fascinating final thought to consider. The digital infrastructure we completely rely on every single second of every single day is largely governed by human negotiation and business policies, which are just translated into BGP attributes. So, if the internet relies on human business policy rather than raw algorithmic speed to survive, what does that mean for the future of new, emerging, decentralized networks? It's definitely something to chew on the next time your data seamlessly crosses the globe in a matter of milliseconds.